Okay, so last time we introduced the idea of what the integral method was all about and how it worked. Today we're going to do an example, and we'll start with looking at the momentum integral technique and then move on to the energy integral technique. So we're going to do an example and solve a problem that we already know the answer to, because it sort of lets us see how close we get to the right answer. So the problem we're going to solve here is a flat plate, right? So flat plate implies that the free stream pressure gradient is zero, and according to Bernoulli's law, then the free stream velocity is constant as well, right? So there's nothing weird going on there. There's no curvature to the surface or anything like that. There's no transpiration, so there's no V velocity at the surface of the plate. There's no shear stress at the outer edge of the boundary layer. This isn't a shear-driven flow. So all those different complications that we could consider with the integral method, we're not here. We're just doing a flat plate laminar flow, so the velocity distribution should be nice and smooth the way it's shown here. And we'll go through the steps that we talked about last time. So assume a functional form for the velocity. We'll substitute that velocity distribution into the integral equation, and we can simplify that equation quite a lot because a lot of the terms will be zero. And what we should get then is an ordinary differential equation that describes how the boundary layer thickness develops, which we'll solve. And this one will be simple enough that we can solve it analytically. And then finally, once we have solved for the boundary layer thickness as a function of position, that will allow us to solve for the shear stress as a function of position. And actually, eventually, we'll get the friction coefficient, and we can compare that to the exact solution, which is called de Blasio's solution. It's a self-similar solution. So those are the steps that we'll go through today. I guess we'll start by just looking again at the integral form of the momentum equation, which is here. So, again, this is without having simplified it at all, and it basically says that the rate of momentum change of the boundary layer, which is this integration here, the velocity distribution, and the pressure force, which is related to the velocity gradient in the free stream, which becomes also a pressure gradient in the free stream. And here we have the potential for momentum being injected at the surface if we have transpiration. And finally, we could have shear at the outer edge of the boundary layer. So for this particular case, right, we are able to eliminate this term here as being not important, this term here as being not important, and actually that term there as being not important. And so we end up with the situation where the only thing that's causing the momentum of the boundary layer to change is the shear force, right? So those two things are acting against each other. So that's our simplified version of the integral equation that we'll use for this problem. So we need to come up then with a functional form for the velocity distribution. So that you have a little bit of freedom there in terms of what the function can be, right? You can choose actually pretty much anything you want as your functional form. Here I've selected a polynomial, right? So this is a second order polynomial. What you're going to find is that it's this part of the process that makes your solution approximate, right? So you can choose very simple functions, and you get math that's basically easier to do because the functions are simple, but at the end you get an answer that's not as good as if you choose more complicated functions. They'll give you harder math, but in the end can represent the velocity distribution better and will give you a better answer, right? So this is kind of actually just an intermediate function. It's third order, right? So, second order. So it's got 1, 2, 3 undetermined coefficients, right, that I get to choose. And the way you choose these undetermined coefficients is you make the velocity distribution do some things that you know it needs to do, right? It's got to represent the actual velocity in the fluid in a boundary layer, so it's not just completely arbitrary. There are some things that it obviously has to do, and the more undetermined coefficients you put into your function, the more things you can make your velocity distribution do that make it look more like the real velocity distribution, right? So here are a list of things that the velocity distribution should do. The more undetermined coefficients you have, the more of these things you can make it do. And actually, this is not a comprehensive list. You could keep going if you want. So sort of starting from most important and going down to less and less important, one thing you would like your velocity distribution to do is go to 0 at the surface of the plate. That's pretty obvious, I think. At the surface of the plate, there's this thing called the no-slip condition, and that says that the velocity at y = 0 has to be equal to 0. So for sure, we'd like that to happen. We'd also like your velocity distribution to go to the free stream velocity when you get out to the edge of the boundary layer, right? So that's another, I think, pretty no-brainer thing for it to do. You'd like at y = delta sub m for your velocity to equal u infinity. If you have more than 2 coefficients, as we do, then there are some other things you could make it do. So, for example, the shear stress at the edge of the boundary layer should be equal to what you know the velocity distribution should have. So for us, the shear stress at the edge of the boundary layer ought to be 0. This isn't a shear-driven flow, right? And at the edge of the boundary layer, the velocity gradient needs to go to 0. And so that's what we would do here. For our particular situation. This is the shear stress evaluated at the edge of the boundary layer, and it ought to be equal to whatever it is for your problem. For our problem, it's equal to 0, right? So that's kind of all we can do, right? Those are 1, 2, 3 different conditions, and I have 1, 2, 3 undetermined coefficients. So I can't force my velocity distribution to do anything else. But if I had, let's say, a third order polynomial, so maybe I had a plus d times y over delta m to the third power, well, I wouldn't be done yet, right? I'd need some other things to enforce. And the next thing to enforce might be that the differential x momentum equation be satisfied at the surface of the plate. So I could require that here's my differential energy, or I'm sorry, x momentum equation. I could require that this be satisfied at y = 0, and that would give me another criteria that I would have for my velocity distribution. If I had, another undetermined coefficient, I could require that this be satisfied someplace else, like at the outer edge of the boundary layer. So you can go sort of as far down the rabbit hole as you'd like. We're going to stop here with these 3 different conditions and force all of those 3 conditions to be satisfied. So starting with the no-slip condition being satisfied at the surface of the plate, that's literally as simple as saying, at y = 0, u has to be equal to 0. So if I take this velocity distribution and plug in y = 0 over here on the right side, that has to be equal to 0 over here on the left side, right? And so I have 0 equals a plus b times 0 plus c times 0 squared, and all that tells me is that a equals 0. So this coefficient here has to be equal to 0, and so I'm left with this velocity distribution here, which I still don't know b and c. So I'll move on then to the next condition, which is that the free stream velocity has to be recovered at the edge of the boundary layer. So at y = delta sub m, I better get u infinity. So if I plug this condition into here, here I'm going to get u infinity, and here I'll put in delta sub m. So that's going to give me 1 equals b times 1, so b times 1 plus c times 1 squared. So that gives me an equation, right? It doesn't tell me b or c alone, but it tells me that b plus c had better equal to 1. Had better be equal to 1. So I should get another equation if I go to the last condition, which is that the shear stress at the edge of the boundary layer needs to be recovered. So this is my equation for that, right? I have to take the derivative of u with respect to y and evaluate that at y = delta sub m and set it to 0. So that's what I did here. Here's my velocity distribution. I plug that into this derivative here, right? So solving this for u, this is what I get. So let's see. The u infinity, I guess, would come out. It's a constant, certainly with respect to y. So the mu and the u infinity can be canceled through because the other side is 0. So I have to take the derivative of this, and I get the first term would be b over delta sub m. The second term would be 2 times c times y over delta sub m squared. But I'm evaluating this at y equals delta sub m, so that's going to end up being 2 times c over delta sub m. So I can again sort of cancel through the delta sub m's because it appears in each term, and I end up with another equation here, which is b plus 2c equals 0. So here's two equations and two unknowns. I just have to solve them together to get b and c. So that's what I've done here. B plus c equals 1, and I subtract from it b plus 2c equals 0. And let's see if I did this right. I have minus c equals 1, so c is minus 1. If I plug c equals minus 1 back up into here, I get minus 1 comes over here, it becomes plus 1. I get b equals 2. So b equals 2 and c equals minus 1, and we already determined that a is equal to 0. So my velocity distribution is right here. So that's a velocity distribution that should look pretty realistic in terms of doing some things that I needed to do. That's the velocity distribution we got for a second order polynomial. I'd like to point out that these have been done for you actually for at least first order, second order, and third order polynomials, and they're shown here. They look a lot more complicated than they are because as you have to put more and more of these requirements on the velocity distribution, then there's more and more potential to have some of these additional terms. So for example, if our shear stress at the outer edge of the boundary layer hadn't been 0, then we would have needed to include that because that would have come into our situation, and that's why you see this term here. For us, we can get rid of this term. We can get rid of this term here, and we get this term, which is exactly what we derived, right? A linear velocity distribution only satisfies two things. It's 0 at the plate surface, so y equals 0, and it's u infinity when y is equal to delta sub m. So it's very simple. A third order polynomial lets you do a whole bunch of things, and so you can see it gets kind of complicated here. But these you can pick up and use if you have a laminar problem. If you plotted these, you'd see that they look more and more realistic. So this is the dimensionless distance from the surface, and this is the dimensionless velocity. So this is the velocity distribution that you get for these different polynomials. So a linear polynomial, a linear function just goes from 0 to 1. It's this kind of not very good approximation of what's going on. We're going to use the second order velocity distribution, which looks a lot better actually. A third order velocity distribution looks even better and actually starts to approach pretty closely this dashed line, which is the actual velocity distribution, right? So as you go higher and higher order, you get better and better results, and you can see why here. All right, so we have our velocity distribution. That's right here. We have our simplified form of the momentum equation, which is right here. We have to take our velocity distribution and substitute it into here and see where we get to. And we actually have to substitute it in two places, right? One place we have to substitute it in is obvious. It's over here where the velocity sits. So our velocity as a function of y has to sit inside of this integral so we can do this integration. But actually over here as well, right? Our velocity distribution implies a certain relationship between the boundary layer thickness and the shear stress, right? So this shear stress that sits over here, this is the shear stress at the surface of the plate, is uniquely related to our velocity distribution as well. So if you remember, the shear stress is mu times du dy, and if I'm talking about the shear stress at the surface of the plate, I would evaluate that at y equals 0. Well, I have a velocity distribution, so I need to evaluate that at y equals 0, and that's what I've done here. I've plugged this velocity distribution into this derivative right here. So mu times d dy of, let's see, u infinity times 2y over delta m minus y over delta m squared. Right? So I got to take this derivative and evaluate it at y equals 0. So let's see, u infinity can be a function of x, but it can't be a function of y, so I got to pull that out. And I take the derivative of the first thing here, I get 2 over delta m. I take the derivative of the second thing here, and I get 2y over delta m squared, but y is equal to 0. So this is 2 mu u infinity over delta sub m. That's what my shear stress is for this specific velocity distribution that we chose. It's actually kind of interesting if you think about it. This isn't that different than what we talked about when we were talking about boundary layers, right? And how shear stress depends on the momentum boundary layer thickness, right? This is somehow related to the velocity gradient at the plate, and the velocity gradient at the plate is at least proportional to u infinity over delta m for a laminar flow. So yeah, where the boundary layer is really small, I'm going to have a really big shear stress. Where the boundary layer gets bigger and bigger and bigger, my shear stress is going to go down, right? So I can plug this shear stress into my integral form of the momentum equation, and that's what I've done here. So the next thing I got to do then is take the velocity distribution and plug it in over here on the left side into the integrand. So this is just a little bit of, I guess, algebra and calculus. So here I've got u squared. So where I have u squared, I'm going to have u infinity squared. Right, I got to bring this over. So u infinity squared times 2y over delta m minus y over delta m squared. And I got to square that whole thing. And then I subtract from that u, which is 2y over delta m minus y over delta m squared, times u infinity. So u infinity appears once for the u, and it also appears here multiplied by u. So I get a u infinity squared there as well. So let's see, I'm going to expand this and sort of make it more understandable, I guess. So I have to square this term here. So if I square this, I get this term squared, which is 4y squared over delta m squared. And then I get 2 times the two terms multiplied together. So minus 4 times y cubed delta m cubed. And then this term squared. So plus y to the 4th over delta m to the 4th. And then this is minus 2 y over delta m. And then minus minus is a plus y squared over delta m squared. And both of these terms have a u infinity squared term, so that's the u infinity squared term. Okay, so I'm ready to do the integration then, right? So every one of these terms has to be integrated from 0 to delta m. So let's see, this is a y squared, so that's going to become y cubed over 4. So you can see here I have 4 over 3 times y cubed over delta m squared. This is a y cubed, so that's going to become y to the 4th over 4, right? So that's what you see here. Y to the 5th over 5 here. Y squared over 2 here. And then y cubed over 3 here. So that's my integration, and I have to apply the limits, which are delta m and 0. So at 0, this whole thing is 0, so I really only have the upper limit. And the upper limit, if I plug into here, you can see every one of these terms, if I plug in y equals delta m, I'm going to have a delta m, right? This is going to be delta m cubed over delta m squared. That's going to be a delta m. This is going to be delta m to the 4th over delta m to the 3rd. That's going to be a delta m, and so on and so forth. So I end up then with all these coefficients, 4 thirds minus 4 fourths plus 1 fifth minus 2 over 2 plus 1 over 3 times delta m times u infinity squared. And if you find the least common denominator of this big mess here, you'll find that it's minus 2/15, if I did that right. So this whole side here is then the derivative of minus 2/15 delta m times u infinity squared. And then the left side, or the right side, is minus 2 times mu times u infinity over rho delta m. So this is the outcome of substituting my velocity distribution into the integral equation, right? Doing the necessary math, and what I get at the end of that is an ordinary differential equation. And the ordinary differential equation describes how the boundary layer grows, right? So this equation here describes how is my boundary layer going to grow as a function of x, right? And it's very flexible in that I can have free stream velocities and other things like that aren't constant in x. They may be doing crazy things, but I can put those crazy things into this equation and figure out how is my boundary layer going to respond, right? And that's what makes this technique actually worth learning, is it's flexible in that way. Okay, so here's where we got to. This is my ODE. For this particular problem, u infinity is constant with x, right? Again, it doesn't have to be, but because it is for this problem, I can pull it out of the derivative. So that's what I've done here. I pulled minus 215 and u infinity squared out of the derivative, and I'm left on the left side then with d delta m dx. And then here I have the right side. This ODE is pretty simple. Actually, it's separable. I can put all the delta m stuff on the left side. So I brought the delta m over here and put it next to the d delta m. I can put everything else on the right side. So here the minus 2's cancel out, and I'm left with a 15 mu. And then one of these u infinities cancel, and I have a u infinity at the bottom and a rho. And then my dx comes over. So I can integrate both these two sides, and I don't run into troubles. So that's what I've done here. This is a definite integral, right? So I don't have a constant of integration because I know that at the lower limit of these integrations where x is equal to 0, my momentum boundary layer thickness is also equal to 0, right? So I'm integrating from the leading edge of the plate. And there's problems where that won't be necessarily true either, right? You can do things relative to that as well, but this is a problem where those two things start out together. So this integration becomes delta m squared over 2, and then on this side I just have 15 mu over rho u infinity times x. So if I solve this for delta m, I've now determined how delta m varies as a function of x, and delta m is a square root function of x, which makes sense because it should diffuse into the free stream, and we know that diffusion goes like the square root of time, which means it's going to go like the square root of x over u infinity, and that's exactly what you see here. This is the square root of 30 times the kinematic viscosity, right, times time. So exactly kind of where we started at in terms of physically understanding what's going on. All right, so this is, I guess, the end of step 3, which is, solve your ODE, figure out how the boundary layer varies with x. And then the last thing is the reason that we care about this boundary layer is because we can use it to calculate the shear stress, right? So here's my boundary layer thickness. I know what it is doing now. I plug it into my equation for the shear stress, which depends on the derivative of the velocity with respect to position at y equals 0. We've already determined that that is equal to this equation here for this particular velocity distribution. So sure, delta sub m dictates my shear stress. If I plug this into here, then I get this equation here, right? And if I simplify it a little bit, it's this right here. So this is my shear stress as a function of x. That might be all I need. That might be what I was going for. I'd like to compare this to the Blasius solution, which is the exact solution for this situation. So I need to express this shear stress in terms of the friction coefficient, which is our dimensionless form of the shear stress, right? So that's the last thing I'll do here is substitute this the shear stress that I just solved for into the definition of a friction factor. So the friction factor is the shear stress made dimensionless by dividing through by rho u infinity squared over 2. So this is this equation here. If I take this shear stress and plug it into here, so that's what I've done here, and simplify it a little bit, I get this equation here, right? So what did I do here? I brought the u infinity squared inside of here, which became u infinity to the 4th, and therefore 3 of these u infinities canceled out with 3 of these, and I'm left with 1 u infinity. The rho came inside of here, so this rho appears on the bottom here. The 2 came inside and became a 16, so you can see sort of where this comes from. So this is, I guess, the square root of 16 over 30, which happens to be 0.730, divided by the square root of rho times x times u infinity over mu, which is exactly equal to the Reynolds number. So my approximate integral solution is 0.73 over the square root of the Reynolds number. The exact solution to this problem, which was derived by Blasius, is called the Blasius solution, or the self-similar solution, is 0.664 over the square root of the Reynolds number. So I think these two things are different by about 10%. I think it's about 10% if you do the math here. So we're off by 10%. If I would have used the linear, so the first order polynomial instead of the second order polynomial, so a simpler form of the velocity distribution, I would have gotten a worse agreement. I would be off by, I think, 15% or so. if I would have gone all the way to a third order polynomial, right, so a more complicated velocity distribution, I'd find that I'm within about 2.5% of this exact solution. So you can see that how accurate you are is dictated by how complicated you're willing to go in terms of the velocity distribution that you start with for these kinds of solutions. So this is an application of the integral method, just sticking here with the momentum form of the integral equation, right? And you can sort of see how this works. So what we'll do next time is go one step farther and look at the thermal form of the integral solution. And again, I hope you already see how flexible this is in terms of dealing with other kinds of complications that you couldn't otherwise deal with, and you'll see even more of that when we go to the thermal to the thermal version of this.